5, 4, 3, 2, 1, action. Okay, so the third and final type of plate boundary we're looking at is transform faults. These can happen either both oceanic crust or in continental crust. When they happen in oceanic crust, they're primarily offsetting mid-ocean ridges. In fact, technically speaking, just about every transform plate boundary you're looking at can be thought of as offsetting mid-ocean ridges spreading at different rates. Now, on the ocean floor, there tend to be a series of cracks concentrated in a small area. The sense of movement on the other side of this is going to be opposite the offset. So even though the ridges over here, it looks like these two ridges are moving away from each other, the actual motion of the lithosphere here is going to be opposite the sense of offset because each of these ridges is generating more new oceanic crust. What these look like at the surface on the continents is things like this. This is very much your San Andreas Fault. It's pretty much running right from where I was standing, right along the foot of this hill, right through where these palm trees are, and off in the distance. And everything this side's going north. Everything on this side is heading southeast relative to where you're standing. Now, the beautiful thing about transform faults is that there's more to them than meets the eye. We're going to take a little tour of some of these features that we find along San Andreas faults on the transform plate boundaries, looking at our own local San Andreas Fault as an example. Action. And here we go. So we're going to look at California locally and zoom in on the state. First things I want to point out before we zoom in much further is you have a mid-ocean ridge up over here. And you have a series of mid-ocean ridges stepping up the Gulf of California. Each with some are easier to see than others, some are more obvious, but trust me, they're there. And then their transform plate boundary, we'll zoom in a little more deeply here. It's going to make landfall right here. It's going to basically hug the coast, but never quite be on the coast. Finally making landfall at Point Arena, crossing Bodega Head, cutting through parts of San Francisco, the Santa Cruz Mountains, doing a wiggle by San Juan Bautista, then heading south. What's beautiful is you can actually see the expression of this fault very vividly, even from outer space. It's one of those prominent things. Finally terminating over here, and then there'll be another set of transform faults. Well, it's popping up on its southern end. And again, your sense of motion is like so. Now here's where I'd like to illustrate one of my favorite things to talk about with transform faults, and that is there's more to them than meets the eye. So what you notice right here, for example, is that you have like what we're going to call oblique compression. That is, there's you have transform right over here with convergence along this stretch right behind LA. And you can also get transform motion with divergence. An example we'll show you a little of when we look at another famous transform plate boundary. But for now, just hold on to that and we'll show you some of the various expressions of this. 5, 4, 3, 2, 1, action! All right, so now we're going to be taking a tour of the San Andreas Fault. It's basically making landfall. First time it makes landfall is right around Shelter Cove, then basically hugs the coast until about Point Arena, where it goes on shore directly, creating the Garcia and Guala River valleys. Stays on shore, stays kind of on shore, jogging finally offshore at some point, making landfall again at Bodega Bay, and then being the center of Tamales Bay, where in the heart of Tamales Bay. So a couple things you notice as we're doing this sort of grand tour is that you see, first of all, we're able to keep a very straight direction on here, which is pretty awesome. And then you're seeing lots and lots of linear features probably all throughout this journey. And even when we're not on top of the fault precisely, we're seeing lots of things move toward offset horizontally. It's forming, for example, and you'll see lots and lots of expressions of this as you head further south. A couple things you notice, for example, are lots of rocks that are offset from one another, lots of linear features connected with it. Zoom out a little bit as we go deeper into Southern California. Down here, you see some very prominent offset rivers. In fact, this is one of the few areas where there's a little bit of oblique extension. So you see these taking place on the San Andreas Fault. Finally, it turns a corner here, makes a sort of abrupt bend, and goes through Pine Mountain look back and the top of the Grapevine Highway. So the thing you see in all this, though, is that lots and lots of there are features, including the spot where I took that picture up in these hills. Finally, it goes along the edge of the Salton Sea and then disappears and terminates probably somewhere around Bombay Beach, where you then have a divergent plate boundary at just about a right angle to the sense of motion on the fault. Action! So perhaps the most interesting part here, though, is that because the fault's not perfectly straight and is not always parallel to the larger plate motion, you have this interesting effect where, on some places, you're going to see convergence along the fault or divergent motion along the fault. So right here, north of LA, along the San Gabriel and San Bernardino mountain ranges, you have some oblique compression. And so what this is going to look like at depth is kind of like so. Five, four, three, two, one, action. So what you see right here in this Google Earth image is kind of a fun thing. So first we're going to draw our San Andreas Fault, both in cross section and in so our fault's running right through here. This is our main plate boundary. And so at depth, San Andreas Fault's going to look roughly like this. It's mostly vertical. And again, remember this side of the fault's coming right at you. This part of the fault is side of it's moving away from you. This is the way we symbolize this is we have a little circle with a dot in it and a circle with a X in it, representing the side of the fault moving away and the side of the fault coming towards you. Now, depth, what this is going to look like is it's going to break this area up into a series of littler faults. You're going to see this sort of expressing itself. Like you can see this one sort of expressing itself as a very low angle thrust fault. You're going to get a whole series of these faults popping up that, in the face of greater compression, are causing material to pop up from the main trace of the plate boundary. Plate boundary says this thing gets squeezed from either side. These beautiful mountains, including the highest mountain in Southern California outside of are all popping up as part of this sort of oblique compression and convergence. Now to see extension, we're going to have to look at another spot. 5, 4, 3, 2, 1, action. So another transform boundary, relatively famous one, runs right through kind of the heart of the Middle East. This is the transform boundary. It runs right through this whole region, the Dead Sea and the parts of Lebanon. I'm not going to point exactly where it ends, but in this fault, the sense of offset is completely the opposite. So now we're going to zoom in on a couple features along this plate boundary of at the western edge of the Arabian Plate. Going up this, first you notice a lot of these narrow seas, just like you saw on here. You notice all these linear features. You also notice there's lots of the rocks on this side look very different from the rocks over here. And there's lots of other faults. But perhaps the most dramatic feature in this whole landscape is this, the Dead Sea, the lowest point on lowest exposed point on the surface of the Earth. So recall your fault in this case, this side is actually the one that's going north more rapidly than this side. So these two sides are going like so. So how did we get this area to be low? Remember, you generally get low-lying terrain when your crust is thin. So if we have a fault running through here like so, there's clearly got to be some feature through here. The fault's making a kind of some kind of jog like so. And this part is being pulled away from over here. That is exactly what is happening. So the way these sorts of things tend to represent themselves is like so. So if we're drawing our plate boundary right through here, and then we know another part of it's going right through up here, what you're probably seeing is something a little like so, where your main trace of the plate boundary is like this. But now, because one side of the plate boundary is being pulled this way, and the other side is being pulled this way, you have some transform with extension. And the way that gets accommodated is through something of a very similar type thing, where you have where you'll have little blocks of crust going down like so, little subfaults along here. As everything gets pulled apart, you have these blocks in the middle that are sinking downwards. And so this way, transform faults have more than meets the eye. And we'll wrap up transform faults by just showing one final example of a transform fault out at sea. This is the Queen Charlotte Fault. Sense of motion along this transform boundary is same plates, Pacific and North America, as the San Andreas. This one's moving southwest. This one's moving or southeast. This one's moving northwest. So what you notice, the big thing you notice about transform faults on ocean crust, they tend to be a little more confined to limited area. But otherwise will behave the same. You could even get parts of the transform system that will behave like extensionally, and places where it will behave compressionally in limited areas. But the overall sense of offset is material being neither created nor destroyed, just sort of sliding past everything. This will sort of wrap up what we do for transform faults. So thank you, and